Okay, so we're going to begin our discussion on bandpass filters. And before we actually begin our full discussion on bandpass filters, we really need to kind of define some terminology and look at what the actual frequency response for a bandpass filter is. Now, remember, ideally, we want the filter response should be the following. So if I have a graph here with frequency and then the magnitude of h at j omega, ideally my bandpass filter is going to look like this, where this is omega c1 and omega c2. But of course we can never have an ideal filter, so ours are going to look more like the following here. So we'll have a flat thing like this. And they might not look exactly like this, but this is the idea. They can have lots of different shapes. But the idea is this is what our more realistic bandpass filter is going to look like. Now, if we think of this as a passive filter, we know that this point here is 0 decibels, because that's where we're at the flat line here. So we're still going to look at the minus 3 dB point. But if I look at the minus 3 dB point, there are 2 points on a bandpass filter that hit my minus 3 dB. And so we're going to define those as omega c1 and omega c2. And so those are still just my cutoff or corner frequencies, is sometimes what they're referred to now, the minus 3 dB points, and they're still half power points just like in our other filters. The difference here is that we've got one for a low frequency and one for a high frequency. And then of course the idea is we're letting all these frequencies in between those 2 points getting passed. So before we actually talk about a circuit and a transfer function that could have this property, let's again label some other information here. Well, one important thing here is this distance right here. We call this the bandwidth of the filter. Now there's bandwidth is used in a lot of different terminology as far as like, and you have to be careful in the application that you're talking about, because in a data sheet for a 741 there's something called the gain bandwidth product, and then you can also talk about the bandwidth for when you're downloading your speeds, what's the bandwidth and everything of that nature, communications. That's not the same bandwidth that we're necessarily referring to here. We're talking about what frequencies get passed through. Now, in those other applications, it still is similar in the sense that you're talking about a range of frequencies, but we're not necessarily talking about a filter application. Okay, so we can see here we're going to call beta equals my bandwidth. And it's very obvious to see a very simple equation to get beta would be omega c1 minus omega c2, and this would be in rads per second. But we could also have beta being fc1 minus I'm sorry, I have these backwards. It would be omega c2 minus omega c1, so we don't get negative numbers. And you could also write it as fc2 minus fc1, but then this unit would be hertz. So both are correct. It's just a matter of what your units are. So okay, so that's not too surprising of an equation we have there. But then we also have something that we call the center frequency. So, and we're not going to have that be omega c. We let omega 0 be something called the center frequency. Come on. There we go. Center frequency. Now, we define this as the geometric mean of omega C1 and omega C2. And so what we have here is omega 0, and this is just mathematics. There is something in mathematics that's called a geometric mean. You also, of course, have your normal mean, which is your normal average, where you add up numbers and then divide by the total. Like if you add up 10 numbers, you then divide by 10, that gets your mean. A geometric mean is instead of adding the numbers up, you multiply and then do the nth root of the numbers that you multiplied together. So in this case, my center frequency is the square root of omega C1 times omega C2. And we can do the same thing again, because this is then just, of course, units of rads per second. And we can do the same thing again here for hertz. We could just say, not omega 0, f0 is the square root of fc2. My hand hit something on the keyboard here. fc2 times fc1. I don't know why I wrote fc2 first. Doesn't matter, multiplication of the order. And of course this unit would just be hertz. Okay, so I'm going to start kind of starring some of the equations here. So this is an important equation. This is an important equation. And then we have one other thing here. We have something that's called the quality factor. And we call this Q. Now, if any of you have ever done anything with soundboards, like if you're in a band or if you've, equalized someone's voice, you can, especially on some of the nice fancy soundboards, like, it can be digitally done, and you can, get filters, that you can design, and one of the things you can adjust is the Q factor on these soundboards, and they're talking about this here, this quality factor, this Q factor. And the Q factor, well, let's look at what the Q factor is by definition here. So the Q factor is the ratio of the center frequency to the bandwidth. So omega 0 over beta, which again, if you had these in hertz, this would just be f0 over beta, but I'm going to emphasize this is in rads per second and this is in hertz. You have to make sure your units line up to do these things. Now what the quality factor does, okay, it's the ratio of the center frequency with the bandwidth. So our center frequency is not necessarily going to be in the middle. That's the other thing that should be pointed. It's not necessarily going to be the exact center. But for purposes of this, let's just say that my center frequency is right there. So let's say that's omega 0. And then this clearly is my bandwidth here, right? And so my Q would be, again, just omega 0 over beta. So if I think about this, well, I have a large bandwidth, so I'm going to be dividing by a larger number here. So my Q is going to be low. And if I have a smaller bandwidth, the Q is going to be higher. So the quality factor gives you an indication of kind of how wide this is. You might say, well, the bandwidth gives me that. Well, the quality factor gives you an essence of how wide it is, and it also gives you some other information that we'll talk about later. All right, but this is, again, just kind of getting all of our equations out of the way. And so, again, we have a set of equations here that are very important to us. Now, we will get equations for omega C1 and omega C2 here in a second, but we have 5 parameters. We have omega C1, omega C2, bandwidth, omega 0, and the quality factor. So there's 5 parameters for a bandpass filter. Now, we can only set, or I should say not set, we can only design for 2 of these parameters. The other 3 are then fixed. And let me do a quick example to illustrate this. So suppose, as an example here, we design a bandpass filter with FC1 is 1 kilohertz and FC2 is 10 kilohertz. So suppose we just designed it like that. So that's it. We've just designed the filter, and of course we have to talk about that in another lesson. But once we have that, we know beta now, bandwidth, because beta is simply FC2 minus FC1, which would be, in this case, equal to 10 minus 1, which is 9 kilohertz. So my bandwidth is fixed at this point. The other thing we have that's fixed is, well, the center frequency. Which sometimes is referred to as the resonant frequency. The center frequency, omega 0, is the square root, well, I don't want omega because we're in hertz. F0 is the square root of FC1, FC2. So this would be the square root of 10 times 1, which, let me pull up a calculator real quickly here. 10 square root, so 3.16 kilohertz. And notice that this is not, as I said, going to necessarily be the midpoint here, because we're not necessarily halfway between. This is the geometric mean, so it's not the mean that you might be used to computing. But now that we know F0, we also know the quality factor is beta, F0 over beta, which is a unitless thing because I'd have 3.16 kilohertz divided by 9 kilohertz, which again, if I just do that, 3.16 divided by 9, 0.351 for my quality factor. So I can only design for 2 things. I can't then design for multiple parameters here. Now, one final thing to end this video is there are other equations here that we can get. So let's write some of our equations down again. So these are equations that we want to know. I might provide these to you. I haven't decided yet. So I'm just going to write the omega version of these. So beta is omega C2 minus omega C1. Omega 0 is the square root of omega C2 minus omega times the square root of omega C1 times omega C2. And then the quality factor is omega 0 over beta. So I've got three equations right here. So these are important. But then we could solve these. We could do substitution and solve for omega C1 and omega C2. And what do I mean by that? Well, we can get an equation here for omega C1 is equal to negative beta over 2 plus the square root of beta over 2 squared plus omega 0 squared. And omega C2 would be beta over 2 plus the square root of beta over 2 squared plus omega 0 squared. So this is another set of equations that would be useful, and that's solving in terms of beta and omega 0, but we can also then use the Q factor, and we can get two additional equations for these. You can get that omega C1 is omega 0 times negative 1 over 2Q plus the square root of 1 plus 1 over 2Q squared. And you can get the similar equation for omega C2, which is omega 0, 1 over 2Q plus the square root of 1 plus 1 over 2Q squared. Now, I didn't go through solving those, but that's literally just taking those original three equations that we have. And the reason that we have these two additional equations is now we have equations that are solved for beta, omega 0, Q, omega C1, and omega C2. So no matter what two parameters we're given, we can find all of the other parameters for a filter.